Thermochemistry is the study of the relationships between chemistry and energy. I alluded to this briefly in a previous video when I said that changes of state are accompanied by a change in heat. This is just one example of the connection between chemistry and energy. Any change, physical or chemical, is accompanied by changes in energy. This video is going to focus first on some important thermochemistry vocabulary, then look at the thermochemistry of physical changes. You need to know and be able to correctly use this vocabulary. Energy is defined as the ability to do work or supply heat. Work, in that definition, is defined as a force acting over a distance. Heat is the flow of energy caused by a difference in temperature. Think of energy as a quantity an object or a collection of objects can possess. Think of heat and work as two different ways that an object can exchange energy with other objects. Energy comes in one of two types, kinetic and potential. Kinetic energy is the energy of motion. Potential energy is stored energy, energy being saved for later. Chemical potential energy is stored energy. It's the energy stored in the particles of a substance. This can be energy associated with the positions of electrons and nuclei relative to one another, the energy of the bonds between all the atoms in the molecules, or attractions between ions in an ionic compound. Chemical potential energy is definitely not the energy associated with the motion of the particles. The kinetic energy of the particles, which we measure as the temperature of the object, is referred to as the thermal energy of the sample. Temperature is a connection between the macroscopic and particulate worlds of chemistry. Temperature is a macroscopic property of the object, but it is a measure of something on the particulate level, the motion of the particles. The kinetic energy of the particles results in the measured temperature of the object. A low temperature means low average kinetic energy, and higher temperatures means higher average kinetic energies. Temperature is not the same thing as heat. Heat is the energy that flows from one object to another because of a difference in temperature. The burning logs in this fireplace are generating heat. The stones and the cat are absorbing that heat. The temperature of the objects determines the direction of heat flow. Heat always flows from an object at a higher temperature to an object at a lower temperature. Imagine these two boxes represent objects at two different temperatures. Object A is red because it is at a higher temperature. That means its particles are moving faster. Object B is blue. It is at a lower temperature. Its particles are moving slower. When these two objects are brought in contact, the faster moving particles of object A collide with the slower moving particles of object B, transferring some of their energy in the process. This is a transfer of heat. The process continues until all the energy has been evenly distributed. The faster particles slowed down some, the slower particles sped up. Now the two objects are at the same temperature because their particles have the same average kinetic energy. Heat is not based solely on the temperature of the object. It also depends on how much of the object you have, as well as its current state of matter. To illustrate, consider these two questions. Which one has the higher temperature? A pot of boiling water or an iceberg? Obviously, the pot of boiling water has a higher temperature. Which one contains more heat? This time it's the iceberg. Because of the sample size, Each particle in the pot of boiling water has a lot more kinetic energy than the particles of the iceberg, but there's significantly more particles in the iceberg. So the total amount of heat contained in the pot of boiling water is less than the total amount of heat contained in the massive iceberg. If you need a bit more help thinking about this, go to YouTube and type in Eureka temperature versus heat. It's a cute, 3-minute video on exactly this topic. A little bit more vocabulary. The system is the material or the process within which we are studying the energy changes. The surroundings are everything else with which the system can exchange energy. What we look at most of the time is the exchange of energy between the system and the surroundings. The law of conservation of energy states that energy cannot be created nor destroyed. The total amount of energy present at the beginning of any process must be present at the end. Energy can be transferred between objects, or energy can change forms, but the total amount of energy must stay the same. Conservation of energy means that the amount of energy gained or lost by the system has to be equal to the amount of energy lost or gained by the surroundings. In this illustration, the system releases energy. The surroundings must gain the same amount of energy. The law of conservation of energy is also known as the first law of thermodynamics. The total amount of energy in the universe is constant. But the truth is, it's a difficult task to determine the total amount of energy in a given system. What's easier and more useful is the change in energy. The first law of thermodynamics could also be said as the change in energy of the universe is zero. The change in energy of the universe equals the change in energies of the system plus that of the surroundings. So the sum of the energy changes in the system and the surroundings must be zero. For that to be true, the energy change for the system and surroundings are equal in magnitude but opposite in sign, just as I discussed on the previous slide. Remember from your past chemistry classes that the word endothermic refers to a process in which heat flows into the system from the surroundings. The system gains heat and the surroundings lose heat. An exothermic process is one where heat flows out of the system into the surroundings. An exothermic system loses heat. The surroundings gain that same amount of heat. Let's turn our attention now to the connections between heat and the physical state of an object. What state a material is in depends largely on two factors: the amount of kinetic energy the particle possesses, which is temperature, and the strength of attraction between the particles. These two factors are in competition with each other. The molecules in a gas have complete freedom of motion. Their particles have enough kinetic energy to overcome all the attractive forces between the molecules. The molecules in a solid are locked in place. They cannot move around. They vibrate in place, but they don't have enough kinetic energy to overcome the attractive forces and move from one position to another. The molecules in a liquid have limited freedom. They can move around a little within the structure of the liquid. They have enough kinetic energy to overcome some of the attractive forces, but not enough to escape from each other. What happens when you add heat to a solid? First, the temperature will increase. An increase in temperature means the particles have more kinetic energy. If you add enough heat, the solid melts. This happens when the particles gain enough kinetic energy to partially overcome the attractive forces. In the same way, liquids boil when heated, because the particles gain enough kinetic energy to completely overcome the attractive forces. Gases can be condensed and liquids can be solidified by decreasing the temperature, removing heat from the system. As the temperature decreases, the average kinetic energy of the particles decreases. The attractive forces between the particles are able to take hold and pull the particles closer together into the denser state. For any of these processes, raising the temperature of an object, changing its state of matter, lowering the temperature, we can quantitatively calculate the associated heat change. Before we look at the calculations, let's talk a little bit more about adding heat to raise the temperature of an object, but not yet changing the state of matter. It's important to understand that objects absorb heat at different rates. If a metal spoon and a wooden spoon are left in the same pot of boiling water, after a few minutes, they won't feel at all the same. The metal spoon will be too hot to touch comfortably, but not the wooden spoon. Why the difference? They should be absorbing the same amount of heat from the boiling water. The difference is the metal and the wood have different capacities for heat, more commonly called heat capacity. This is the quantity of heat required to raise the temperature of a system by 1 degree Celsius. Metals tend to have low heat capacities. When a metal absorbs even a small amount of heat, its temperature changes quite a bit. A more useful quantity for chemists is specific heat, the amount of heat needed to raise the temperature of 1 gram of an object, 1 degree Celsius. As I said before, if an object has a low specific heat, that means only a small amount of heat is needed to noticeably change the temperature of the object. Something with a high specific heat must absorb a good bit of heat for its temperature to rise. Think about how nice a pool of water feels on a hot day, especially compared to the scorching concrete beside it. If the pool and the concrete have been exposed to the same amount of heat from the sun all day, why are their temperatures so different? Because water has an unusually high specific heat, so it can absorb a lot of heat without changing temperature very much. Concrete has a much lower specific heat. The same amount of heat changes the concrete's temperature quite a lot. So I've just reviewed some important thermochemistry vocabulary and concepts. The next video in this unit will review the calculations associated with the thermochemistry of physical changes.